Hello students, welcome to the online class for automobile component design. This subject is present in your 5th semester diploma syllabus for automobile engineering department. Let me first introduce myself. My name is Tanmoy Kundu, assistant professor, Department of Automobile Engineering, Dr. Sudhit Chandra Sur, Degree Engineering College, Kolkata. Here you see this is our course objective to impart knowledge of fundamental concept of machine design applied to automobile components, to impart exposure to standard course of practices, CAD and use of design data book, to impart knowledge concerned to automobile component design. Next come to the course outcome. So at the end of this course students will be able to analyze, identify and use these following important outcomes. Next come to the lesson plan. So this is all about the lesson plan and this is prepared as per the syllabus under West Bengal State Council, where we see the module number 1 and module number 2 I have already covered, and in the module number 3 just go for the sub module number 3.6. So today I shall be discussing on the design of piston pin, that is the Gaussian pin. So let us start our today's topic on piston pin, lecture number 28. The piston pin, that is also called a Gaussian pin or wrist pin, is used to connect the piston and the connecting rod. So that is very important aspect, that the piston, if you can imagine, if you can just remember the diagram that I have shown you earlier in the previous lecture, that there is a provision for space provision for the Gaussian pin. So that Gaussian pin is basically used to connect, to make a bridge, to create a bridge in between the connecting rod and the piston. It is usually made of hollow and tapered on the inside. So it is tapered in the inside and also in hollow. The smallest inside diameter being at the center of the pin as shown in figure 1. So just look at this. So this thing as you see, this is completely tapered. So at the very center the tapering is the most and the inside diameter is very least at the very center. Okay. The piston pin passes through the bosses provided on the inside of the piston skirt and the bush of the small end of the connecting rod. So here you see that piston pin basically passes through the bosses, and that bosses is provided on the inside of the piston skirt. So you can see this way the relation has been established between the, or the connection has been established in between the piston and the connecting rod. So one side of the piston pin connects with the piston skirt, and another side just entered through the bush of the small end of the connecting rod. So here you see this is how the connection established in between the piston and the connecting rod. The center of the piston pin should be 0.02 D to 0.04 of D, where capital D means it is the bore of the cylinder, or it is the outside diameter of the piston. Above the center of the skirt, in order to offset the turning effect of the friction and to obtain uniform distribution of pressure between the piston and the cylinder liner. So this is all about the different aspects, different reasons for which that there is a provision for offset the turning effect in order to reduce the frictional effect and also to distribute the pressure uniformly. The material used for piston pin is usually case hardened steel alloy containing alloying materials like nickel, chromium, molybdenum, vanadium, etc. And they are having the tensile strength from 710 MPa to 910 MPa. This is the piston pin that I have already shown you earlier. Now this is full float type piston pin, because piston pins are classified into several categories. Now the connection between the piston pin and the small end of the connecting rod may be made either full floating type or semi floating type. So depending upon the connection established, so the piston pins are classified like full floating type or the semi floating type. So this is the figure 2 is for the full floating type piston pin. This one is the piston pin. So this is the circlip, this is the piston boss, and the whole part is the piston, as you see. This is the circlip, this part is the circlip. So if you see this cross section, so it will be looked like this circlip. Okay. In the full floating type, the piston pin is free to turn both in the piston bosses. That means this one is the piston boss and the bush of the small end of the connecting rod. Okay. So this has the capacity to turn both within the piston boss and as well as in the small end of the connecting rod. Okay, this is the thing for the circlip part. The end movement of the piston pin should be secured by means of spring circlip as shown in figure 2 in order to prevent the pin from touching and scoring the cylinder liner. So there is a provision for the spring circlip also. So as there is spring, so it can prevent the pin from directly come into the contact with the cylinder liner, and there is no direct metal to metal contact or any direct you can say rubbing action happened. No direct rubbing action happened between the cylinder liner and the piston pin. Now next come to the semi floating type piston pin. Here you see this is the semi floating type piston pin. In the semi floating type, the piston pin is either free to run in the piston bosses or and rigidly secured to the small end of the connecting rod, or it is free to run in the bush of the small end of the connecting rod and is rigidly secured in the piston bosses by means of a screw. So what is the difference between the semi floating and floating? So where we see in case of the floating type piston pin, the piston pin is free to turn both in the connecting rod end and also in the connecting rod as well as in the piston end, okay, piston bosses. But here you see in the semi floating type piston pin, it is not at all free to move both in these two ends. Okay, so it can either turn in the connecting rod end, and if it is so, then it will be totally closed. It will not be free to rotate or turn in the piston boss. So either piston boss or the connecting rod. So among these two, at any of this part it will free to rotate, but in another part it will not be permitted to rotate. Okay, so this is the biggest difference between the semi floating type and floating type piston pin. So this is the diagram. This is locking screw, small end of the connecting end. This is the piston pin. The piston pin secured to the small end of the connecting rod. Okay, the piston pin secured to the boss of the piston. Okay, this way. The piston pin should be designed for the maximum gas load or inertia force of the piston, whichever is larger. So design aspect is that the piston pin should be designed for the maximum gas load or the inertia effect or inertia force of the piston. So whichever will be higher, so based on that the piston pin will be designed. The bearing area of the piston pin should be about equally divided between the piston pin boss and the connecting rod bushing. Okay, so the bearing area should be equally divided, because piston pin is basically the bridge in or the connection in between the connecting rod and the piston. You can say the piston boss. Okay, piston pin boss. So and the bearing area shared by the piston pin must be equally shared in between these two parts, that is the connecting rod and the piston. Thus the length of the pin in the connecting rod bushing will be 0.45 of the cylinder bore or the piston dia, allowing for the end clearance of the pin. The outside diameter of the pin, that is D0, is determined by equating the load on the piston due to gas pressure P and the load on the piston pin due to bearing pressure PB1 at the small end of the connecting rod bushing. So these are all of the design clauses. The mean diameter of the piston bosses is made 1.4 of D0 for cast iron piston and 1.5 of D0 for the aluminum piston, where you see that the D0 is the outside diameter of the piston pin. Okay, the piston bosses are usually tapered, increasing the diameter toward the piston wall. Let us let us go for the numeric the mathematical part. So let D0 is the outside diameter of the piston pin in millimeter. L1 is the length of the piston pin in the boost of the small end of the connecting rod in millimeter. So its value generally taken 0.45 of D. D means it is the cylinder bore, or it is the outside diameter of the piston. PB1 is the bearing pressure at the small end of the connecting rod bushing in Newton per millimeter square. Its value for the bronze bushing may be taken as 25 Newton per millimeter square. So these are all about the design values, and that value we have to remember. Now we know that load on the piston due to gas pressure or gas load, so it is pi by 4 d square into P. Load on the piston pin due to bearing pressure or bearing load, so it is like bearing pressure multiplied by bearing area. So bearing pressure is PB1 and bearing area means it is simple a rectangle like having dimensions D0 and L1. So D0, that is the outside diameter of the piston, multiplied by L1, that is the length of the piston pin. Outside diameter of the piston pin multiplied by the length of the piston pin. So we have got projected area for the bearing pressure. Okay. Now from equation 1 and 2, just go to the equation 1 and 2. Now from this equation 1 and 2, the outside diameter of the piston pin may be obtained, because just to balance these two equations, equation 1 and equation 2, so by equating these two equations we can find out the piston pin diameter, that is D0. Okay. The piston pin may be checked in bending by assuming the gas load to be uniformly distributed over the length L1 with supports at the center of bosses at the two ends. So in the figure 32.8, so we see that particularly the pressure, the gas pressure is uniformly distributed over the length L1. So this is the thing. So total find the length between the supports. So L2 supports means this is the support. The L1 means this is the length of the piston pin. Okay, D0 means this is the diameter of the piston pin. Here L2 means here two supports are provided. So each support take the load like P by 2 obviously. So capital D means it is the piston outside diameter. So this the length in between these two support, the gap in between these two supports is L2. So L2 equal to, we see that is L1 plus D by 2. Okay, so L1 plus D minus L1 by 2, that means after arranging it is coming like L1 plus D by 2. So that expression we have to remember. Okay. Now maximum bending moment at the center of the pin. So at the center, this is the very center of the piston pin. So at this position we see the bending moment will be like PD by 8. So this expression we have to remember as well. For the value of the maximum bending moment at the center of the pin, it is PD by 8. We have already discussed that the piston pin is made hollow. Let D0 and Di be the outside and inside diameter of the piston pin. D0 and Di. So this is D0, that means it is the outside diameter of the piston pin. Di means it is the inside diameter of the piston pin. So section modulus Z. As you know, the section modulus Z, that is equal to I by Y. If you see, that is the formula. For the circular part, I equal to, you know, pi by 64 D0 to the power 4 minus Di to the power 4, like this. And divided by Y. Y means it is the simple D0 by 2. So this way we have got the result like z equal to pi by 32 d0 to the power 4 minus di to the power 4 divided by d0. This is the section modulus for any hollow circular section, that is the hollow piston pin. So its section modulus is like this. Now we know that makes maximum bending moment. We also know that the bending equation m by I equal to sigma by y. Okay, so we see that m equal to sigma multiplied by I by y. Once again, I by y means it is section modulus z. So bending moment equal to, we see this is the bending stress multiplied by the section modulus, okay, that is z. So m equal to z into sigma b, that means bending moment equal to, we see it is the bending stress multiplied by section modulus, okay. So it is coming like pi by 32 d0 to the power 4 minus di to the power 4 divided by d0 multiplied by sigma b. So here this sigma b is the allowable bending stress for the material of the piston pin, and it is usually taken as 84 MPa for case hardened carbon steel and 140 MPa for heat treated alloy steel, because we see that the piston pin are mostly made of the case hardened carbon steel or the heat treated alloy steel. So for these both two types of material, I have mentioned the allowable bending stress value. Now in your numerical, so it is not always expected, or it is not or always there will the value of the sigma will not always be mentioned in your numerical. So in that case you have to remember this data, okay. So assuming di equal to 0.6 of d0, the induced bending stress in the piston may be checked, okay. So di is generally assumed that the inside diameter of the piston pin shall be 60% of the outside diameter of the piston pin. So that is why it is written as di equal to 0.6 of d0. So from this equation also we can find out the induced bending stress value. So these are all about the different types of design guidelines for designing the piston pin. So another names of piston pin I have told you, that is Gaussian pin or wrist pin, okay. So several types of numericals may arrive in new semester questions as well from this piston pin chapter. So you have to know all the mathematical formulas for determining the piston pin length, piston pin dimensions, especially piston pin length, that is the L1, the outside diameter d0, the inside diameter di, like this. So these derivations may directly come from the relations of the bending moment, and this is how we can determine the values like this. And along with the mathematical formulas, as I have told you earlier, this particular chapter on IC engine material design, component design, so we have to know the different values for the stress figures for different materials used, okay. So here also for the hardened carbon steel material, the sigma b value is mentioned. For the alloy steel material, the sigma b value is mentioned, so that values we have to remember as well. Sigma b value, pb1 value, that is the bearing pressure value. For the bronze bushing is also mentioned, 25 Newton per millimeter square. So these are the all about the different data along with the mathematical formulations that are very very much required to remember. So these are all about the piston pin design. So please, you are all advised to go ahead with this particular contents, along with you should practice the numericals, and also you have to remember the type of materials used for the piston pin, okay. The I have told you the the alloy steels are used. So in the alloy steel, the alloying materials mostly will be nickel, chromium, molybdenum, vanadium, like this. Okay. So just also try to chalk out the difference between the full floating type piston pin and also the semi floating type piston pin. So depending upon the free turning inside the piston boss and the connecting rod bushing. Okay, so depending upon that, the freely turning ability, whether it is there or not there, so depending upon this, we see that full floating type and semi floating type both are classified. So in the semi floating type, we see that either it can freely turn into the connecting rod bushing, and in that case it will be completely locked in the piston bush. Okay, but in case of the you see that it is a full floating type of piston pin, it can completely turn, or it can freely turn in the both in the connecting rod bushing and the piston pin bush. Okay, piston bush, connecting rod bushing and piston bush. So this is all about my today's lecture on the piston pin design. So you are all advised to read all those important mathematical formulas along with the materials, along with the design data for the individual material, so that any numerical that can be asked from this particular chapter, so it can be very much answered. Okay, so thank you very much.